Mr. Qasan Al-Hasnawi, do you have my voice? Do you have my voice? Okay, thank you. In this session, we follow other concepts in product measures, and the following result provides an example of an algebra that we will exploit. Let S, we read this proposition for you. The set of finite union of measurable rectangles is an algebra. We see the definition of algebra in the previous session. R is called an algebra, so that R have these three properties. Empty set belong to A. R is closed under complementation, and R is closed under finite union. Okay. Now, the set of all finite union of measurable rectangles is an example of algebras. Suppose X and S and Y and tau are measurable spaces, so that S is a sigma algebra on X and tau is a sigma algebra on Y. Then the set of finite unions of measurable rectangles in this sigma algebra, S tensor tau, is an algebra on this set. And B, every finite union of measurable rectangles in this sigma algebra can be written as a finite union of these shown measurable rectangles in S tensor tau. And its proof is easy, and we see a special case of this proposition in the previous example. Okay, let A denote the set of finite unions of measurable rectangles in this sigma algebra. Obviously, A is closed under finite union. That we say in the previous session, we see completely its proof by this. For any finite element of A, we see that its union is an element of A. But in this example, we work with intervals, and in this case we have measurable rectangles. The proof is similar. And this is its proof. To verify this claim, note that if we consider A1, A2, AN, C1, Cn in S and this in tau, then this is a finite union of measurable rectangles. Okay, and this is another finite union of measurable rectangle. The intersection of these two equal to this, and this equal to this, and we know that this is a measurable rectangle, so that this is a finite union of measurable rectangle, so that if we consider any two elements of A, please note that we denote A for the set of all finite unions of measurable rectangles, okay? So that any element of A has this form, a finite union of measurable rectangles, this and this, and the intersection of two arbitrary elements in A equal to an element in A, so that A closed under two or finite intersection. A is closed under finite intersection. Now if we consider A in S and B in tau, then we see that the complement of this measurable rectangle equal to this, and this is a finite union of measurable rectangle, union of two, okay, measurable rectangle, so that this is a finite union of measurable rectangles 1 and 2. Hence the complement of each measurable rectangle is in A, because written as the union of two measurable rectangles. Thus the complement of a finite union of measurable rectangle is in I. See De Morgan, and the result in the previous paragraph that A is closed under finite intersection. Okay. In other words, A is closed under complementation, so that the proof is complete, because A is closed under finite union. A is closed under finite union. It's trivial. A is closed under finite union, and by this fact that A is closed under finite intersection, we see that A is closed under complementation, so that A is an algebra. And for the proof B, note that if we consider two measurable rectangles, then we see that the union of these two rectangles equal to this, and these measurable rectangles are disjoint, mutually disjoint, okay, are mutually disjoint, so that we see that the union of any two rectangle can be written as disjoint measurable rectangles. The equation above write the union of two measurable rectangles as the union of three disjoint. These two written as the union of three but disjoint, okay? Three disjoint measurable rectangle in this sigma algebra. Now consider any finite union of measurable rectangles. If this is not a disjoint union, then choose any non-disjoint pair such as this, okay, of measurable rectangle in the union and replace those two measurable rectangles with the union of three disjoint similar this. See, three disjoint measurable rectangle. Iterate this process until obtain a disjoint union of measurable rectangle. Okay, this is trivial that we can prove this. Every finite union of measurable rectangle in this sigma algebra can be written as a finite union. Any two elements of measurable rectangles that have intersection, non-empty intersection, can be written as three disjoint one. Okay, three disjoint one. Okay, and we have the definition of monotone class. Dear students, welcome Mr. Mashadi, Muhammad Al-Khafaji and other students. Dear students, do you have my voice? Don't have any problem? Give me example. Which example, Mr. Ghassan? An example for this proposition. You want an example for this proposition, Mr. Al-Hasnawi? In the previous session, we see this example. This is almost an example of this proposition, and its proof is very similar. Okay, this example is similar to the proof of this proposition, but you can take many examples. For example, our proposition is this: if x and s and y and 2 are measurable spaces, and A equal to the finite union. For example, we can consider these finite unions. Okay, I from 1 to n, such that n is a natural number or even 0, You can call 0 or not because empty set is an element, and in S or 2 AI belong to S and BI belong to 2. Okay? The set of all finite union of measurable rectangles. Then A is an algebra on X time bars. Okay? This is our proposition. But as an example, we can see we can consider X equal Y equal real numbers and S equal to equal sigma algebra of Borel sets. Then, for example, this is an element of A because A is a finite union of rectangles, and for example this is an rectangle 1 times, for example 2 3 union 2 multiplied by 2 3, and for example n multiplied by 2 3. This is an element of or algebra. Or for example, you must consider this multiplied by this, and you can take union by any other rectangle. Please note that all of these are in our sigma algebra. Okay, this must be in S. All of this must be in S, and all of these must be belong to another 2. Okay, another sigma algebra or sigma algebra on Y, that we consider these two equal to Borel sets. Okay, all of these are Borel sets, so that this is an element of A2. Mr. Al-Hasnawi this example is good for your question or not. Mr. Al-Hasnawi. Okay. Okay. So that this is an general proposition for any two measurable space if we consider finite union of measurable rectangles. This is an algebra. This algebra in this case is the finite union of product of Borel measures such as this. Finite union, okay? Finite union. And many other examples. Okay? And we have the definition of monotone class. Suppose W is a set and M is a set of subset of W. So that M is a subset of the power set of W, P of W. Then M is called a monotone class on W if the following two conditions are satisfied. One, for any decreasing sequence in M, E1, E2 up to the N, increasing, okay? The union of the sequence belonging to M, and for any decreasing sequence in M, such as this, the intersection of the sequence belong to M. If we have these two properties, we say that M is a monotone class. Monotone. Because any increasing or decreasing sequence in M have union and intersection in M. Okay? Clearly, this is a good example. Clearly, every sigma algebra is a monotone class because we know that in any sigma algebra we have these two properties. For any increasing sequence we have this, and for any decreasing. And really we have these two property for any sequence in M, not increasing sequence, and we have this property for any sequence, not only for decreasing sequence if M is a sigma algebra. Okay, we have these two properties for any sequence, so that for increasing and decreasing sequence this condition holds true. Okay. However, some monotone classes are not closed under even finite union, as shown by the next example. Example, a monotone class that is not an algebra. Suppose A is a collection of all intervals in R. All intervals. Then A is closed under countable increasing union and countable decreasing intersection, so that A is a monotone class. The set or the collection of all intervals. Thus, I is a monotone class. However, I is not closed under finite union and A is not closed under complementation. Thus, I is neither an algebra nor a sigma algebra. Okay? It is very clear that if we consider A the set of all intervals x equal to r and a, the set or the collection of all intervals. Okay, A is a monotone class. Monotone class. Okay, but A is not an algebra. This is very easy because, for example, we see that these two are in A, but its union not belong to A because this is not an interval. A is the set of all intervals. This is not an interval. Okay, this is not an interval. So that, okay, this is not an interval. For example, 1, 2 and 3, 4. The union of these two is not an interval. So A is not closed under finite union so A is not an algebra, and this shows that A is not a sigma algebra. Because it is very easy that if A is a sigma algebra, then A is an algebra, and these two are equivalent because we know that P then Q equal to the negation of Q then the negation of P. Okay, we see this frequently. Any sigma algebra is an algebra. In the other word, if A is closed under countable union, A is closed under finite union. If consider any finite element in A, then this finite union equal to n countable union. You can consider a n plus 1 up to the n equal to empty set, and this is must be belong to A. If A is a sigma algebra, must be closed under countable union, so that this must belong to A, so that this is must be belong to A. This equal to this finite union. Okay, if A is a collection of subset of some set, then the intersection of all monotone classes on W that contain A is a monotone class that contain A. Thus, this intersection is the smallest monotone class on W that contains A. The next results provide a useful tool when the standard techniques for showing that every set in a sigma algebra that a certain property does not work. Suppose A is an algebra on a set W, then the smallest sigma algebra containing A is the smallest monotone class containing A. The smallest sigma algebra equal to the smallest monotone class. Let if A be a subset of PW power set, the set of all subset of W, and M equal to intersection of all monotone classes, we can consider MA, okay? All M such that M is a monotone class and A is a subset of M. This is our index set, okay? These two properties. This monotone class is the smallest monotone class. MA is a monotone class because if we consider any increasing sequence in MA, such that we have this arrange, then for each monotone class this sequence must be belong to M for each M in this class. Okay, in this class H, for example, for each M in H. And so that since M is an monotone class, since M is a monotone class, for each M in H, this union must be belong to M, because M is monotone class, and we have this arranged for this sequence, and for this is hold for each M. We see that this union must be belong to the intersection of M. M belong to H. Okay, so that this set is closed under increasing sequence, union of increasing sequence. And similarly, if AI is a sequence in MA and this is an decreasing sequence, then we see that for each M in this index set, this sequence must be belong to M, and by these reasons again, for each M in H, this intersection must be belong to M2, and this shows that this intersection must be belong to the intersection of these M's. M belong to H. Okay, and these are infinity. Okay, so that MA is a monotone class, and it is very easy that this MA is the smallest monotone class that contain A, because we consider the intersection all of these M's, so that MA is the smallest monotone class that contains A. It is very trivial too, because if M is a monotone class, and A is a subset of M, then this M must be contain MA, because MA is the intersection of all of these monotone classes. Okay, This intersection is a subset of all of these monotone classes. So that MA is a subset of all of these M's. Now in this proposition, we say that if A is an algebra, then the smallest sigma algebra containing A is equal to the smallest monotone classes. We denoted this sigma algebra by SA, I think, okay? So that if we have these notations, MA equal to the smallest monotone class contain A and SA, the smallest sigma algebra contains A. This proposition says that if A is an algebra, then MA equal to SA. And we know that this equal to the intersection of all M, that M is a monotone class and contains A and this is equal to the intersection of all S, for example, such that S is a sigma algebra and contain A. Okay? So that this proposition says that if A is an algebra, then the smallest monotone class contains A equal to the smallest sigma algebra contains A. And this proof is very easy. Let M or MA by I symbols denote the smallest monotone class containing A. Because every sigma algebra is a monotone class, M is contained in the smallest sigma algebra containing A. Okay? So that this for the proof of this, we see that S or SA is a monotone class. containing A, so that MA must be a subset of SA, because this is a smallest monotone class containing A. This is n monotone class. This is the S smallest. Okay, we see that any sigma algebra is a monotone class. Okay, this is a sigma algebra, so that this is a monotone class, and we know that A is a subset of this and this. Okay, so that MA is a subset of SA. To prove the inclusion in the other direction, first suppose A belong to A, and let E equal to this. We omit the proof, the, the following proof, because it is easy, but you must check some relations. Please read this proof and write the converse of this inclusion for me. Okay, SA please read from our textbook. Okay, okay. Dear students, we have a problem in voice, okay? Do you have my voice now? Do you have my voice now? Dear students, do you have my voice? هل عندك صوتي؟ Okay, sorry, I don't know. Okay, let me repeat again. A measure mu on a measurable space is called finite if mu of x is finite. And I saw that mu of x is finite equal to this statement. For any element of S, mu of A must be finite, because if we have these conditions, A is a special case in S, so that mu of x must be finite. And if we have these conditions, since any element of S is a subset of x and mu is monotone, mu of A must be less than mu of x, so that if this is finite, this amount must be finite too. Okay? Do you have my voice, dear students? Dear students, do you have my voice? Okay, and for sigma finiteness, mu is sigma finite whenever there exists a sequence in S such that x equal to the union of this sequence, and for each k mu of xk is finite. For example, Lebesgue measure on R is sigma finite because we can write R real numbers as the union of these intervals, and the Lebesgue measure of each interval is finite. Okay? Dear students, we can continue in next session. Do you have any questions? Dear students, do you have any questions? Do you have any questions? Dear students, do you have any questions? هل لديك أسئلة؟ Thank you for your attention, and goodbye for now. Goodbye.